right, good morning. Well, lots of news today, I think. One thing is we've got our, what do they call it? Day off anyway. I can't remember what it was called. Since we don't have a spring break, they give us one day off. And it's class time next time. So no class Thursday. Uh, 4:15. It's day off replacing our spring break that we lost. However, we do have an exam coming up. Last midterm exam of the semester, exam 4. That'll be on Thursday, 4/22. It's during the regular class time by email as usual. It'll be open book and open notes like before, just no personal help. And the exam will cover chapter 8. I've already got the practice exam out there, so this is 9 days to get ready for it. The good news is that it's only over sections 8.1 through 8.4, and we aren't doing much out of 8.4, so we'll say 8.1 through 8.3, and polar graphs. A little bit on that out of 8.4. This is really easy. It's not very many sections, and so you have a chance to do better on this exam. I think this will be the easiest exam. Not a lot of sections, 9 days to prepare. The practice exam is already on D2L, right? So I just put it up this morning. File those problems. When we come back a week from today, we'll do review. So any of those problems you can't do, ask me. Ask me in my office hours in the meantime, but bring them to class on Tuesday. We might do some new material too. We don't do nothing new next week after getting a day off on Thursday and then review on Tuesday, exam on Thursday. I want to do something new. So possible new material. Got complex numbers. All those things are coming up. Practice these problems. You have a whole week before we meet again to look at these and then ask me some questions and fun office hours. Any questions you want to ask on this or on what we did last time? Okay, you should have your let's say this then. For today, we want to look at polar coordinates. The rest of the semester is going to be applications of trigonometry, not strict trigonometry itself. So if you don't do so well on this, it's not such a big deal. You can pick it up later as you take later classes. But this will help you in ensuing classes. These are used a bunch in calculus, for instance. If you've seen them in here, you'll do better. They're also used in other classes. So let's say this. In plane, and I'll put X and Y, call that you can take any point that has coordinates x0, y0 obtained by dropping a perpendicular to the x-axis and see where it lies. And if that point on the x number line is x0, then that's the x coordinate, right? And then if you drop a perpendicular to the y-axis and it intersects the y number line at y0, these are supposed to intersect at their 0 points, these number lines. And that's the coordinates of the point, x0, y0, right? So that was one way of identifying every point in the plane. Every point in the plane had a unique perpendicular you could drop, hence unique coordinates. And every pair of coordinates correspond to a unique point. An alternative that's sometimes nice when you have a radial symmetry, like gravity has radial symmetry, right? If there's an object out here, it doesn't matter on what angle it's at. It only matters how far away it is from the sun, or whatever gravitational object. You may prefer this kind of coordinate systems. For that reason, astrophysics and lots of other things that have radial symmetry, like machine parts and so forth, we'll use these coordinates. Instead of taking these perpendiculars, we'll take our distance from the origin and we'll call it R. Say, how far is it from here to here? Well, it's pretty easy actually, right? Because we know this distance is absolute value of x0. Put x0 because we're in the first quadrant, but in general it's absolute value. And this distance here is absolute value of y0. And so what is R, the length of this one by the Pythagorean theorem? It's square root of this squared plus this squared, right? It's square root of x0 squared plus y0 squared. And we'll say, well, actually, that's an arbitrary point. Let's just call it, say its coordinates are x, y, and we'll say for an arbitrary point, x, y, the distance from the origin is square root of x squared plus y squared. Now, that doesn't uniquely identify the point. That just says how far away it is. If I also include this angle turning counterclockwise to this line segment from the origin to the point, theta, now I know exactly where it is, right? I can turn through this angle theta and then move out this distance r, and there's a unique point determined by turning through the angle and moving out the distance theta. And how shall I specify theta? We know how to specify r. Well, we notice from this little triangle here again that the tangent of theta is the opposite over the adjacent side. Tangent theta is y over x. And so we have these equations for x and y, excuse me, r and theta. We can put r equals that square root, or we could square both sides and just say it's the Pythagorean theorem correctly. R squared equals x squared plus y squared, and tangent theta equals y over x. Tells you how to find r and theta given x and y coordinates. All those equations one. I can also go the other direction, right? Suppose I'm given angle to turn through and how far out I go. I can find x and y, right? I can drop this perpendicular, make this triangle. And what do I know that this displacement is here? I say displacement because it could be negative. If the point is over here, then I drop it over x might be negative. X is then hypotenuse r times this length here, cosine theta. This is actually true in any triangle, right? Any right triangle, you have a hypotenuse r and an angle theta. In order that this side over this side be cosine theta, this must be r cosine theta, right? So that this over this is cosine theta. In order that this side over this side be sine theta, this side must be r sine theta. So in any triangle, this is true, and this is actually useful. They use this in first year physics if you ever take that, which is required for engineering and all sorts of other applications. So this is true in any triangle. We can draw it right up here. This side must be x equals r cosine theta, y equals r sine theta. So now from that picture, we observe that we can go back the other way, make some blue equations here, and say going the other way, x must be equal to r cosine theta, y must be equal to r sine theta. So if I've given r and theta, I can find x and y back. These are conversion equations between what we call rectangular coordinates or Cartesian coordinates after the famous philosopher Descartes, who was also a great mathematician, right? And he got analytic geometry going, geometry with coordinates, which allowed Newton and Leibniz, other people to come by and invent the calculus. And calculus got started because coordinates were available due to Descartes, the coordinate system, and other people were developing it too. But now what we do is we say, since we can, by any r and theta whatsoever, identifies a unique point, we just turn through that angle and go out that distance. We'll just call those polar coordinates, right? And actually the origin in the xy plane is, when you're using polar coordinates, is technically called the pole. So sometimes I'll refer to this as the origin, sometimes as the pole, depending on the application. But we can uniquely identify a point by putting down an ordered pair of r theta instead of x, y. And these are like radar coordinates, right? I mean, the radar, it's at a certain angle, a certain distance out, it's that kind of thing. The only thing is radars tend to spin clockwise, or our angles are measured counterclockwise, right? All right, so there's the conversions given x, y rectangular coordinates. You can find r theta, the polar coordinates, and given r theta, an ordered pair of radius from the origin and angle theta, you can find rectangular coordinates x, y, goes back and forth. And actually, these are easier than these. And can you see why? There is a little ambiguity. If I say tangent theta equals y over x, there's actually two angles between 0 and 360 degrees that have that tangent. Remember this, the angle in the opposite direction, this one, which is theta plus 180, has the same tangent. So you have to decide, I drew this in the first quadrant, but there are points in the third quadrant too. If the point is in the third quadrant, you can't just say, oh, theta is the arctangent of y over x, the inverse tangent, because the inverse tangent is always in quadrants 1 or 4. And if your point is in quadrant 3, you'll get the wrong angle. So you have to, in this calculation, be very careful to put theta in the correct quadrant. If the angle is in quadrants 1 or 4, for positive r, you can say theta is the arctangent. If the angle is in quadrants 2 or 3, you have to say the angle is arctangent plus pi. Straight angle, right? Or arctangent plus 180 degrees if you're doing degrees. So you have to add 180 degrees to the arctangent if you're in quadrants 2 or 3 using positive r. Now it's actually a little more confusing than this, because for generality of applications, there are some applications where it's convenient to allow r to be negative. What? How can a distance be negative? Well, what we do is we say in that case it's not the distance. Minus r, and here's what we do. Say, just to make things harder for you right now. It's actually so you can do more applications, but it makes it a little more confusing. Also, we allow r less than 0 with theta equal the opposite direction to the point. To identify a point. In other words, suppose it's a first quadrant point again, just for simplicity. I have this point x, y in rectangular coordinates. I can consider this line segment out here again, and then go the opposite direction here and let theta be this angle, which goes to the opposite way, the opposite direction x, y, and then r will be minus this distance. And so we'll say, in this case, r equals minus the square root of x squared plus y squared, and minus the distance. And again, it turns out that tangent theta is y over x. If you draw the unit circle in here, do this. This is the point x, y. So let's draw the triangle the same size here. And we can consider the point minus x minus y directly on the other side. What's the tangent of this angle? Well, it's this point would be minus x over square root x squared plus y squared. This one would be minus y over square root x squared plus y squared. That's the corresponding point on the unit circle. If you divide by the roots on square, it gives you the point on the unit circle. It's the same direction. And you can tell if you take this square plus this square, you get 1, so it's on the unit circle in the same direction because it's just a multiple of this. But this point now, if you take this over this, right, you get if the tangent of theta is the y coordinate over the x coordinate of any angle in the unit circle, tangent to this theta is minus y over square root x squared plus y squared, y coordinate on the unit circle, over minus x over square root x squared plus y. Things are getting bad, aren't they? And these square roots cancel, minuses cancel. You get y over x. You observe, right, that the opposite angle has the same tangent. You just go to the unit circle definition that the tangent of the angle is y over x of the unit circle. This is the point on the unit circle that goes in this direction. When you divide it, you still get y over x. So it's the same tangent as this one. You just have to pick the angle in the third quadrant if the point's in the first quadrant, right? So we'll again have this relation, tangent theta is y over x. So again, for r less than 0, we can take r equal minus the distance to the point, minus square root x squared plus y squared. And tangent theta, again, is equal to the y coordinate over the x coordinate, regardless of which quadrant you're in. And these two equations, again, describe the point. Well, if you square this one, you get this equation again. So equations 1 still hold. In other words, these equations hold whether you let r be negative or r be positive. All right. And so these equations hold in all cases. And also equations 2, if you figure it out in these other quadrants. Equations 1 and 2 hold in all cases. Where x is not equal to 0 for the last equation. Unless you get a division by 0. But actually, if x is equal to 0, the angle is easy to find, all right? Because if x is 0, then you're on the y-axis, and you know the angle is is pi over 2 or 3 pi over 2. So it's actually not hard to find theta there. I guess I should put this exception. It's just you choose r negative and theta the opposite direction, or r positive and theta the same direction is the point. That's how it works. All right. So you observe that there's at least 2 polar coordinates for every point. Even though each pair of polar coordinates identifies a unique point, there's at least 2 ordered pairs, r theta, that will identify the point, one with r positive and one with r negative. Moreover, there's actually an infinite number of polar coordinate pairs, because if you add any whole number of rotations, you get the same terminal ray and also the same point. So even though each r theta identifies a unique point, there's an infinite number of ordered pairs r theta for the point, unlike rectangular coordinates where it's just 1 to 1 both ways. Now it's screaming for an example, right? Because you're probably totally confused with the r. It's not very hard. Let's try this one. These aren't so bad. Example, find polar coordinates for rectangular coordinates x equals -1, y equals plus square root 3. If those are my coordinates in the xy plane, what are the polar coordinates? And I think it's not a bad idea to draw the picture. You don't have to, and in the long run, you'll probably not do it so much because it takes more time. But for now, it's probably real insightful if you visualize this a little bit. It's really, really helpful when you're first getting going. So let's go over to -1 here, and plus square root 3 is about 1.732, so it's most of the way to 2. Here's square root 3, and we're about right here. Right, so there's the point, -1 square root 3. The rectangular coordinates, right, drops to these 2 points. Now, what are the polar coordinates? I'm going to find polar coordinates 1 with r positive, right? And I say there's 2 coordinates, one with r positive, one with r negative. R equals 0, then there's you can take any theta you want because it doesn't matter what direction you go. You're still at the pole, at the origin, right? So with r greater than 0,
Excuse me, Professor.
Yeah.
Could you move the camera over a little bit? I'm having trouble seeing.
Oh, I'm at the very end. Sorry about that. I had to get it just right. I may have a little problem here. Things sometimes won't zoom out. System is odd. Oh, it did. Oh, good. It actually works again. Let's try that. Is that better? I hope. There we go. Thank you. Let me know if this blue is getting too faint or something too. I need to get some more pens in this room. Let's try and find polar coordinates for this point with rectangular coordinates -1 square root 3. And the idea is you could just do this. I said these are the equations, but what people do in practice, if they want r positive, they just take r equals the square root of x squared plus y squared by 1 with r positive. R equals the square root is the square root of -1 squared plus square root 3 squared is square root of 1 plus 3. Oh, square root of 4 is 2. So this point is exactly 2 units from the origin. If I draw this line segment out here, r is 2 units out. Now, how about theta? I solved that by solving tangent theta equals y over x. And what turns out to be important in higher courses is that when this is a special angle, you find it exactly. Don't just give a decimal approximation. Don't say, oh, it's arctangent, and give a decimal. They want you to find it exactly. So I'll say tangent of theta is y over x is square root 3 over -1. And the temptation is now to say, oh, theta is the arctangent of minus square root 3. There's a couple ways to do this. One way is just to say, I know what ratio that is on the unit circle. This is square root 3 over 2 over -1/2, right? That's a point on the unit circle with the same ratio. I divided top and bottom by 2, so it's the same quotient. But now this is y and x on the unit circle. This must be y, or on the unit circle, sine theta. This would be cosine theta. And I know what angle that is. I can now sketch it on the unit circle. And if y is square root 3 over 2, almost a 1, and x is -1/2, I'm at this point right here, draw the line segment, and I observe from the reference triangle that this is a pi over 3 60-degree angle. That makes this one 2 pi over 3. Maybe that's theta. The trick, however, is there's 2 angles that have that theta, right? Because it can also be this. I can take minus this one over minus this one. I can take minus square root 3 over 2 or plus 1/2. And then this would be y and this would be x. And so in that case, I go down here to minus square root 3 over 2, like see that it's too small. Minus square root of 3 over 2 on this axis, plus a half on this axis. Sketch the reference triangle, say, oh, this is a pi over 3 angle. It follows that theta must be 2 pi back up pi over 3. Right. 6 pi over 3 minus pi over 3 is 5 pi over 3. So evidently, since tangent is this, theta could be pi over 3 or 5 pi over 3 within one rotation. Right? So which one is it? It's supposed to be pi over 3 or 5 pi over 3, right? Well, it has to go into the same quadrant when r is positive. That was the idea. For a polar coordinates, you can either take the distance to the point, a non-negative number, and the angle to the line segment, or you can take r minus the distance to the point and go to the opposite direction. Both of them give the point. So for r greater than 0, I want to go to the point. I have to be in quadrant 2 with x negative and y positive. It's this one. This one is in quadrant 2. So I'll say my first polar pair, according to equations 1 here, leave these up in the middle. R equal to theta equals, oops, I wrote pi over 3, it was 2 pi over 3. I must, 2 pi over 3. Theta equals 2 pi over 3. And this ordered pair is called polar coordinates for the point. Polar coordinates are these. However, we said you could always do for everywhere but the pole a negative coordinate, right? What if we took now B polar coordinates with r less than 0? Well, now we want to take r equal minus the square root x squared plus y squared minus the distance to the point. Now we already computed square root x squared plus y squared is 2, so we just take r equals negative 2. We also have tangent theta equals y over x. It's the same thing, but now we want to go into quadrant 4, the opposite quadrant. All right, this point is in quadrant 2, so we want to take theta to be the opposite quadrant when r is negative. Theta has to be 5 pi over 3, the opposite quadrant. Is quadrant 4. So now my polar coordinate pair with r negative is just negative 2, 5 pi over 3. These are both perfectly good coordinates to go for the same point. Now I want to, in part C, say what are all polar coordinates? I told you there's an infinite list, and this is why. What do we need for all polar coordinates? We need to have the angle either to the point or directly opposite, and r either positive or negative. And if you think about r, it can only be these two values. It can only be the distance to the point or minus the distance. We just have to choose theta and have the right terminal ray. And so all polar coordinates are the first one, 2 pi over 3 plus any whole rotation. We write that as 2k pi, where k is any integer, and then with nothing after the decimal point. Or we can have r negative with 5 pi over 3, and any coterminal ray would have plus 2k pi. So once you find one polar coordinate pair with r positive and one with r negative, you just put plus 2k pi in the angle, and that's all polar coordinates. That's it. That's how you do polar coordinates. For rectangular coordinates, you find the distance to the point, the angle into the same quadrant, add 2k pi if you want for any k. You take minus the r with the opposite angle by adding pi to it, and then plus 2k pi. That's all you have to do to find polar coordinates for a point. And a lot of times you can just look at it and tell. Here's another example, an important one because it takes an exception to what we just did. What are polar coordinates for the point with rectangular coordinates? Uh, 0, -5 of that. This one, you don't use equations. One, you don't need them. You can start that way if you want, but it's easier just to visualize in your mind. This goes down here to x equals 0, y equals -5. 1, 2. And you just say, I know what distance that is from the origin. It's 5 units down the y-axis. I can root some square of these. 0 squared plus 5 squared minus 5 squared square root is 5. But it's easier just to look at it and say it's 5 units, right? So 5 equals r. If I get polar coordinates for r greater than 0, I'll turn to the angle. And then the angle is what? It's pi over 2, pi, 3 pi over 2, right? Pi over 2, pi over 2, and pi over 2 is 3 pi over 2. The wrong direction here. And so one pair of polar coordinates, just without even a calculation there, is 5, 3 pi over 2. What are polar coordinates this time with r less than 0? Well, now I want to go to the opposite angle, so I can pick pi over 2, right? And go minus this distance 5. So I just put minus the radial value I got here, and the opposite angle, pi over 2. Here's polar coordinates with r less than 0. I didn't have to do any calculations, right? Now, what are all polar coordinates? Oh, this one's going fast. All right, all polar coordinates are just these plus 2k pi. Mostly we'll work in radians because in calculus it turns out to save a conversion factor over and over and over if you use radians instead of degrees. But if you go on to be a surveyor or an astronomer or something like that, you might do more degrees. So we will from time to time do degrees. All right, so 5, 3 pi over 2 plus 2k pi, where k is any integer, gives all polar coordinates for the point. And then the other one, minus 5 pi over 2, any with r negative plus 2k pi, gives all polar coordinates with r negative. Here it is. Maybe I should put down here just to be clear what an integer is. K can be 0, 1, minus 1, 2, minus 2, and so on. Any integer. That's what you do if the point lies on the y-axis. Then the tangent equal y over x doesn't make sense. You just look at it and see, right? Then finally, I mentioned this before, but we should actually draw the example once. What are polar coordinates corresponding to the origin of the xy plane? Well, I just put r equals 0, and that forces me at the origin. Theta is arbitrary. Doesn't matter what direction I pick, it's still the pole, the origin. And so 0 theta for any theta. Polar coordinates for that. Well, we converted rectangular to polar. Sometimes people will give you polar coordinates and ask you to convert it to rectangular. Let's do some of those. Convert these polar coordinates. And I'll tend to give you special angles on these, and I want you to convert them exactly in that case. You can certainly convert non-special angles, and we're going to do that too. But suppose the polar coordinates are 4, 7 pi over 6. Now I want to convert those to rectangular. How can I convert the other way? That's just equations 2. I erased the number, but they're still here. This was equations 2. Now we'll say 1 converts from rectangular to polar, but equations 2 convert the other way. And these are just plug and chug, I call them. You just plug them in and see what you get. There isn't any ambiguity like there was here. What quadrant is it in? Right? You just plug it in here. X is equal to r cosine theta is 4 times cosine 7 pi over 6. You just have to evaluate 7 pi over 6 in a unit circle and you're done. There's no difficulty. There's only one answer, right? There's only one coordinate pair x, y that identify any particular points. You always get one x, y coordinate and you just plug it in and see what it is. All right. So 1 is 7 pi over 6. I'll run to the unit circle and say 7 pi over 6. There's 6 pi over 6 is pi. Pi over 6 more is 7 pi over 6. So it's like that. It's got a 30-degree angle here over 6. So this side is square root of 3 over 2. This side is a half. Coordinates of this point then are minus square root of 3 over 2 minus a half makes the cosine and sine of that angle. So the cosine must be minus square root of 3 over 2. Well, now you want your 4 to cancel 2 out here, and we'll call this point minus 2 square root of 3. Here's the x. All I did was plug in, and I have to, since it's a special angle, I can evaluate it exactly in the unit circle. Now, y by equations 2 is over sine theta is 4 times sine 7 pi over 6. Well, I've already got my sine on the unit circle is minus a half. So it's just 4 times minus a half. So the one unit circle does the whole thing. 4 times minus a half then is negative 2. We observe the rectangular coordinates then is just one case, minus 2 square root of 3 minus 2. That's it. Plug in and use the unit circle. Now, I can erase these. I think you can remember them. What if these are not special angles? Right? It becomes a little harder game. Equations 1. There are some other angles you can do exactly with the half angle formulas and so forth. It's not worth me throwing those at you. I think you know you can do them. Instead, what I'll do is we'll say I'll only have you evaluate them exactly if it's a special angle. And any other angle, you just run to the calculator. And here's just by example. Suppose I want to find polar coordinates for the point with rectangular coordinates minus 12, minus 5. How about that? The polar coordinates for those rectangular coordinates. This is x and this is y. Now I just go to equations 1 and I say by equations 1, r can be by equations 1 choosing r greater than 0. Remember, you can choose it either way. We have r is plus the square root x squared plus y squared. Oh, this is the square root of 144 plus 25. It helps in this class to remember your squares, doesn't it? 144 is the square root of 169. Maybe you remember is 13. So I picked some easy numbers here where you actually get a whole result. A lot of times you'll get a decimal here. And Then I have tangent theta equals y over x. So which quadrant do I pick? I pick the same quadrant as the point. The point is negative x and negative y is in quadrant 3. Well, I solve this theta in quadrant 3. Well, let's see. I could try. There's two different directions. One of them is always theta equals the arc tangent. Y over x is arc tangent. Well, this way. Is arc tangent minus 5 over minus 12. And if I run that in the calculator, I can cancel the minuses if I want because it's the same arc tangent. Let's try that. Arc tangent of 5/12. See what we get. Make sure your calculator's in radians if I ask for radians here, of course. I think I messed it up here. I had to convert it to radians here. All right. So now, arc tangent 5 divided by 12 is 0.39479, blah, blah, blah. But there's another possibility, right? What's the other arc tangent? Or the other solution? The other possibility is theta is the opposite direction. It could be arc tangent pi over x plus pi. This may not put you and maybe you want an answer between minus pi and pi. This may not do that for you, but it will give you a correct answer. Let's take that one, and all I have to do to get this one from the first one is add pi. So I'm going to put plus second pi on my calculator equals, and now I don't need to recalculate the arc tangent. But if you just push the plus button and take whatever on the screen, it adds to it. And so I put plus pi, and I get this immediately. 3.53638. Other stuff. And so these are the two answers actually within one rotation. 0 to 2 pi. We could round these off. These are rounded numbers here. I could just put it there to 5 decimal places. Right? Very accurate, right? Now, which one is it? Well, you go back to the original point. You say this is in quadrant 3. You can tell from the number which one's in quadrant 3 and which one's in quadrant 1. But it's easier than that. The arc tangent always comes out in quadrant 1 or quadrant 4. So the arc tangent is wrong. Right? This one is going to be in quadrant 1, actually. Opposite the original quadrant. Right? So if this is in quadrant 3, the other angle will be in quadrant 1. So I don't want this one. With R positive, I'm going to choose this one. So my answer on this one in decimal, if I'm asked for 5 decimal places, is for R greater than 0, I choose 12.00000 if you like, or just 12 exactly. And then 3.53638 is the polar coordinates to 5 decimal places. How about R less than 0? What are the polar coordinates now? Well, you just put minus r, so you take minus 12.00000, and you take the other angle, 0.39479. That's it. You calculate the arc tangent, you calculate the arc tangent plus pi. You choose the angle that goes into the quadrant when r is positive. You choose the angle into the opposite quadrant when r is negative. And there's an infinite number of answers. You can add 2k pi to either one of these and get all the coordinates. Sometimes people like you to give an answer between 0 and 2 pi. I won't ask that. I think let's just say for the exam, pick any theta you want that is correct, right? And so you can put this one plus 2 pi if you want, or this one minus 2 pi if you want, whatever angle goes to the right point. Questions on that one? That's a little more awkward. Here's your keystrokes on most calculators. It depends on the calculator, of course. But to get this one, you simply say second tangent, because up above is the arc tangent. And then you put in y, you might as well, since the minuses are going to cancel anyway, just put 5 divided by 12 instead of minus 5 divided by minus 12. And if your calculator doesn't close parentheses, you might want to put a parenthesis in here. You will have to put it. Some calculators you'll need the parenthesis. And we'll put enter. And that's it. Arc tangent 5 divided by 12 gets you that one. The other one, to get that, once you have the first one, you just push plus and it brings up the answer that's on the screen. Second, whatever button has the pi over the top on my TI calculator, it's the caret key. Yeah. Push enter. And that'll give you, that's how I did those very quickly. Right? So arc tangent 5 divided by 12 plus pi. Easy as that. Okay, now there's some other problems. We can plot points given in polar coordinates on polar graph paper. These are not real popular, but you do see them once in a while just because polar coordinates are used a lot. And what the idea is, you just turn to the angle, really easy, turn to theta, move out r, when r is positive, or turn opposite theta and move out distance absolute value over negative. So if I say this one, and I'm surprised that these seem so easy, and yet I have people miss these in the exam, so you have to practice them. Plot, here's problem 5a, the point minus 2 pi over 3. How do I plot that? What I do is I first turn to the angle pi over 3, about like that at 60 degrees, right? By the way, I should point out, let me draw it here. Polar graph paper has some of these drawn in to help you. It also means I expect an exact plot. So it will put out on this one. Some of them also include 45-degree angles. Here's a 30-degree angle, 60-degree angle. It splits each quadrant into three pieces: 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, and 330 degrees, like that. And then it will put the radius. Here's a radius of 1, radius of 2, radius of 3, and so on. Now it says plot this point minus 2 pi over 3. So I turn to the angle pi over 3, which is right here, 60 degrees. And then I back up 2 units, 1, 2, and I plot it right here. That's that point. Turn to pi over 3, back up 2 units. Let's try another one. That's polar graph paper. Pi over 2. Pi over 2 is a quadrantal angle, right? So you turn to pi, and then I'll back up, and then I'll move forward 5 units, right? Since R is positive. 1, 2, 3, 4, 5 up here. Next circle. That's the point 5 over 2. And then let's plot, let's do it red, I guess. Plot point minus 2 pi over 4. Well, pi over 4 is halfway between these, right? It's not sketched, but you have to put it exactly in between. Here's the angle theta equals pi over 4, not part of the polar graph paper. And then I go 2 units backwards, so I put it right here, halfway between these two. That's plotting on polar graph paper. Pretty easy. Turn in the angle and then go either the distance out or minus the distance out, depending on, or either distance out the same direction if R is positive, distance out absolute value of R if it's the opposite direction. Now, finally, we want to convert equations. To convert equations, these are a different game. You use either equations, 1 or 2. Whichever is easier. They both work with care. Because you sometimes, in order to convert these, need to multiply through by R or square both sides or something. Also, we'll say, be careful algebraically multiplying through by a number like R, or let's say multiplying through by any number. You might multiply through by X in some cases, or squaring. It's a real interesting game. It seems so obvious, and it is, but like I said, the devil's in the details. That's when you get to, when you get to the details, then there's actually some tricky stuff in here. So here's consider this one. Suppose I want to convert this one. What kind of equation is this from algebra? 2x plus 2y equals minus 3. I know how to graph this really easily. I would like to review just a little bit of your graphing from algebra geometry. What does that graph look like? Can I sketch that really easily? Now I'm going to convert it to polar coordinates, see what it looks like in polar coordinates. Easy? I don't know. What you do is you look at it, and sometimes you don't want to answer. I know ax plus by equals c is the general form of an equation for a line. Any equation of this form with a and b not both 0 is a line. Every line can be put in this form. So this is, they call it the general form for an equation of a line, or a linear equation, x and y. So this is always a line. The line always has such an equation. You can write it that way. All I have to do to plot this one from algebra is find 2 distinct points, put down my straight edge. It's no harder than that to plot it. I'm going to say sketch this. It's easy, right? I'll just put the easiest one is put x equals 0 and find y, put y equals 0 and find x. Not only are you less prone to make mistakes, but now you find the all-important intercepts. You're always looking carefully to see if you plotted it right, right? So if I put x equals 0, then this falls out. I've got 2y equals minus 3. Y must be minus 3 halves, right? So the 2 times minus 3 halves is negative 3. Now if I put x equals y equals 0, then this falls out. I've got 2x equals minus 3. X must be minus 3. So I can plot this easy as can be. I just go out to halfway between minus 1 and minus 2 right there, and halfway between minus 1 and minus 2 here, right here. Put down my straight edge. There's the line. 2x plus 2y equals 3. I wonder what equation of this line looks like in polar coordinates. It's really easy. Whenever you have an equation of rectangular coordinates, all you really have to do is put in equations 2, and we'll say by equations 2. Sometimes it's easier to use equation 1 depending on what it has, but you can always just use equations 2 for an equation given in rectangular coordinates. We'll say you just put in for x r cosine theta, you put in for y r sine theta, that's it. I should check to make sure they did this in the answer, but in applications, what turns out to be the case is you want to generally write r as a function of theta, because you're thinking of turning to the angle theta and moving out r, or turning to opposite theta and moving out absolute value of r. And so a lot of these problems, they want you to solve for r as a function of theta. I can't remember on this one. Check and see what it did. The answer wasn't given on this one, alas, but on part C, it did write r as a function of theta. And I should say, be careful multiplying through or squaring, and I should have said one more thing, or dividing also cause problems. We do have to do that sometimes. What you'd like to do here is solve for r, and maybe I'll do this, ask you to write r as a function of theta, just by convention. Just like you write y as a function of x, you like to write r as a function of theta and turn to the angle and go out. So let's go ahead and factor this out. Say this is 2r equivalently times cosine theta plus sine theta equals -3. And then I can divide through and say that r equals -3 over twice cosine theta plus sine theta. So there's r written as a function of theta. Now you see there's a problem. When I divide through, maybe cosine theta plus sine theta is 0, right? If that's equal to 0, I have a division by 0, so I should have just kept this equation, right? Well, it's actually okay. Because, let's see. Yeah. This equation didn't have such a solution anyway. If cosine theta plus sine theta was equal to 0, you can't make 2r times that equal -3, right? So I know that there is no solution with cosine plus sine equal to 0 to this equation. Here, therefore, that's equivalent to this one. All right, so I'll rewrite that like that. That being said, there is a point. Let's see. No, that's right. Yeah. So there was no solution where this is divided by 0. So these two statements are equivalent. You do have, if you think about it, the only angles that make cosine theta plus sine theta equals 0 at this angle and this angle, and you don't have any points right on the line that are at those angles. This goes out forever without giving you a point on the line. So there is the polar equation r is a function of theta for this line. So that's all there is there. Now, let's look at this one. This is a little trickier. See, I'm going to do all of these and do the homework without looking at what we did in class, and then go back and look at what we did in class and see if you can figure it out. What if I put lid off too long there? Part B, x plus 2 squared plus y plus 3 squared equals 13. I wonder how that compares. Well, one thing you can do always is replace x with r cosine theta, replace y with r sine theta, and that always works. Sometimes there's a lot of extra algebra. It'd be easier to use equation 1. But equations 2 always works converting rectangular to polar. So let's do that. I have this equation. And then the object is to simplify it and see if I can solve for r. So I've got from here, but you have to FOIL, be careful, right? It's r squared cosine squared, square of this one, plus twice this times this by FOIL, right? Because multiply this out, r cosine theta plus 2 times r cosine theta plus 2. You don't get just this squared plus this squared. You get this times this is this, plus this times this, plus this times this is 4 r cosine theta. This times this is 2r cosine theta, and there's another one outside and inside, and then last is 4. So that's this first one squared out. And then I have the second one squared out. R squared sine squared theta plus, again by FOIL, 2 of these, 3r sine theta makes 6r sine theta, plus 3 squared is 9, and the whole thing has to add up. Well, now you can see how to simplify it a little bit. This one's a little harder, isn't it? What is r? If I group these two here together, I'll say this is r squared times cosine squared plus sine squared. Algebra is coming back to bite us again. And then plus r times 4 cosine theta plus 6 sine theta. And then plus 13 here equals 13. Just cancel. All right, I can put 0, right? Subtract 13 from each side of this. And now let's see what I've got. I've got cosine squared plus sine squared. You want to remember the Pythagorean identity. This is just 1, right? Sine squared plus cosine squared is 1, no matter which order you add them in. So this becomes r squared plus r. I can factor 2 out of here and call it 2r. 2 cosine theta plus 3 sine theta. All equals 0, right? Subtracting the 13s and writing that as 1. Now I can solve for r, can I? You can do it with quadratic formula if you want, or you can do it by factoring. You can rewrite this as r times, right? Pull out the greatest common factor is r in these two terms. Terms are things that are added together. The greatest common factor is r. R times r plus twice cosine 2 cosine theta plus 3 sine theta. Equals 0. So you can see it's actually kind of a tricky game here, right? Now I've got it factored. How can I make a product equal to 0? A product is 0 if and only if at least one of the factors is 0, right? So I have from here either this factor is 0. Factors are things that are multiplied together, or this factor is 0. So I write them equivalently as r equals 0, or r plus twice. Oh, maybe I didn't need to factor that 2. It almost looks harder, but 2 cosine theta plus 3 sine theta. 0, and I can solve these, right? The first one is already solved. The second one, if I subtract this over, I've got r equals, let's just write it this way, minus 4 cosine theta minus 6 sine theta. So it actually breaks up into 2 equations, each of which is pretty simple. This is how I write r as a function of theta for this one. By the way, what is this? Think about it, it's actually a circle, right? It's a circle. Remember, x minus x0 squared plus y minus y0 squared equals r squared. This is a circle of radius square root 13 at the point minus 2 minus 3. Numbers that are subtracted here. This circle has this answer. And now something interesting happens here. R equals 0 is the pole, the origin, right? And if the origin is a solution of this one, I don't need this one after all. Can I make minus 4 cosine theta equal plus 6 sine theta for some angle theta? In fact, I can. This includes the point where 6 sine theta equals minus 4 cosine theta. It's the point where tangent theta divided by cosine divided by 6 is minus 2/3. Right? There is such an angle where theta will be tangent theta will be minus 2/3. I just pick that angle and then I find out what r is. And r, that will make r equal 0, right? If tangent theta satisfies this angle, then these will be equal, and this will be 0, r will be equal 0. Then r equals 0. So the pole is already included here. If the pole is included, I can throw this out. Now I've actually thrown out, this is the tricky part, some coordinate pairs r theta here, right? Because r equals 0 here, theta could be any angle. So r equals 0, theta could be any angle and satisfy this equation. But r equals 0 is the same point regardless of what theta I pick. So if there's, even though here, tangent theta has to be minus 2/3 to get r equals 0, this still includes the pole r equals 0. So I don't need this equation because the pole is already included here, even if not all the same angles of the pole. Therefore, the whole thing reduces to just one equation. R equals minus 4 cosine theta minus 6 sine theta gives all the points on this circle. There's your final answer. It's tricky. If you got this, I'd give you all but 1 point, or maybe I give you all points. But I'd like you to see this in general, how this can be a little subtle. And then the last one is actually very important because this comes up in lots of classes where you have to do this one. Again, you take a look at these when you go. 6C, this, been doing problem 6 here. X squared plus y squared equals 3x. This one reduces very nicely too. What you do here is, it's easy enough to use equations too. You can always just plug it in and plug in r cosine theta squared plus r sine theta squared equals 3 times r cosine theta, and this works. You just have to do some trig identities. But what's easier is to use both 1 and 2. On the 2, when I see x squared plus y squared, I remember by equations 1, that's just r squared, right? And then x is r cosine theta. There it is. Now you'd like to write r as a function of theta, so you just want to be careful. Now write r as a function of theta too here. The easiest thing is to divide by r and just say r equals 3 cosine theta. There's the answer. Is it right? It is, but you have to be careful, right? When I do here, r was a solution. I can divide both sides of an equation by any non-zero number, but I have to be careful. If I have x squared equals x, there's 2 solutions, right? X equals 1 and x equals 0 are both solutions. But if I divide through by x and get x equals 1, now I've lost one of them. So when you can divide both sides by a non-zero number, but if I divide both sides by a variable, I have to check the case, make sure that variable was 0 to make sure I didn't throw out a solution like I did here. So that's the trick here. In this equation, I divided by r. I have to check what if r equals 0. Is it still a solution here? Maybe it's like this problem here, and I threw out a solution. Well, let's see. R squared equals 3r, right? Because r equals 0 is certainly a solution here. Both sides are 0. But now here, if I choose theta equals pi over 2, then the right side will be 0, and r equals 0 is a solution. Okay. So the pole is a solution. I've lost some ordered pairs because here r could be 0 and theta could be anything. Here I have to take theta equal pi over 2 or 3 pi over 2 or some, add 2 pi to that to make r equal 0. But I do get r equals 0 for at least 1 point. So this includes the pole. It includes the same point set. Even if not all the same ordered pairs are theta, it still includes the pole. So this is where I want to leave it. This is the final answer. So the moral of the story here is use both equations of 1 and 2 for speed. Just to write these equations 1 here and equations 2 here. You can divide through by r as long as you don't throw out the pole. Right? So there's 6C. All right. Finally, you may want to convert these polar equations to rectangular. These are quite important too, because one of the reasons you use polar coordinates is to make your life simpler when things have radial symmetry, right? That's the whole purpose of introducing these things. You don't want to just be able to do different numbers, right? Equations. You want to have some purpose to it. So let's do this. 7A, convert polar to rectangular equations. And sketch them. This one's under sketch 2. If I get a chance, I'll go back and sketch this and show you what that one looks like. It's kind of tricky. I forgot to sketch this. Actually, maybe I should. Usually these are easier to sketch from the rectangular conversion. So you convert it this way, but you sketch it using the rectangular coordinates. This actually comes out to be a circle. We can do that next time. Short on time. This one. Part A, r equals -4. How do I convert that to rectangular coordinates? This is a harder game going to rectangular from polar because you don't just have r equals theta equals. You have r squared equals and tangent theta equals. And so you have to do it with carry. You have to get one of those things in equations 1 or 2. Again, you use both equations, but just you have to put it in that form. So how can I get something that's in equations 1 or 2? Well, if I square both sides, I can say this is equivalently r squared equals -4 squared is 16. And so I know what that is. R squared by equations 1 is x squared plus y squared equals 16, which I'll write suggestively as 4 squared. So I get it into something I see in equations 1 or 2, and then I apply equations 1 or 2, in this case 1, whichever one's easier. And I say, I know what this was. X squared plus y squared equals r squared is a circle of radius r equals 4 at the origin. Right? Remember this equation for a circle at the origin, x squared plus y squared equals r squared. So I can sketch this readily. I just go like that. Oh, wait a minute. When I squared both sides, I introduced new solutions. Now r can be 4 or -4. Did I introduce new solutions? Well, I introduced new r values, but no points in the plane are new. Because r equals 4 is also this circle, right? R equals 4 is all points at a distance 4 from the origin with theta arbitrary. It's the same circle. If you square both sides, again, you get r squared equals 16 in the same circle. So this introduced no new points by squaring in this case. You just have to be careful and check that I introduced new solutions or not. And there's no new points, even though there's new values of r. So it's tricky like that. All right, now How about this one? B, suppose I want to sketch theta equals pi over 4. It's important to be able to sketch r equal a fixed number is always a circle at the origin of radius absolute value of this number. That's what you learn, right? This is all points at a distance 4 from the origin of theta arbitrary, because you go to arbitrary theta back up 4 units. It's all points at distance 4 from the origin. So you can intuitively see this is a circle radius 4, just like this is. And then squaring it verifies that. So theta equals pi over 4, how do I sketch that? Well, what you're doing intuitively is you're turning to an angle theta equals pi over 4. And then I can go out any distance r, right? R is arbitrary, so I get all these points, but that's not it. What are the other points? R is allowed to be negative, right? So I can go opposite direction any distance I want. And so what I get is the whole line at an angle pi over 4 in the xy plane. This is the sketch. You just turn the angle pi over 4, and theta equals a number is always a line through the origin. R equals a number is always a circle of whose radius is that absolute value at the origin. Easy. So R equals constant, theta equals constant. Memorize those, because that's what you do polar coordinates for, is things like circles and lines to the origins. Now we can convert this easier, or you can see from the picture that this is the line y equals x, although it might be a harder one on the test. Let's say here's how you can convert it. You can take the tangent of each side. Tangent theta equals tangent pi over 4. This is one we memorized. Tangent pi over 4 is -1. Now when I have tangent here, I can write that by equations 1 as y over x, and I got y over x equals -1. Multiply by x, I've got y equals -x. Oh, tangent pi over 4 is +1, sorry. Yeah, y over x is 1. Anyway, y equals x is the line, of course. So there's the derivation of y equals x that I intuitively do. All right, try all of the problems on 8.3. That's 1 through 7. We did most of them, and we'll do some review in these next time. Thank you so much for coming in today.